We're going to look at U-substitution, some basic examples of that today. So think about when we learned about derivatives, we learned a rule called the chain rule, which was taking the derivative of composite functions, so a function within a function. So if I write out the chain rule for derivatives said I was differentiating a function within a function, so f of g of x. And we talked about how we had different layers, and so the derivative of f of g of x, I take the derivative of the outside layer first, which is f prime, keeping the inside layer, times the derivative of the inside. So I would end up with f prime of g of x times g prime of x. Well, U-substitution is a method for integration, so finding antiderivatives, when I have something that would apply to the chain rule, but now I'm looking at an integral, not a derivative. So let's say I'm starting with the integral of f prime of g of x times g prime of x dx. Well, this is the derivative that resulted from chain rule. So when I take the antiderivative, this result is going to go back to the original function, which the original function just goes back to f of g of x. And then because it is an indefinite integral, of course I have to write plus c behind my answer. Now, when we first look at this, it looks very complex. It has a lot of different things happening here, a lot of parentheses, variables. And so U-substitution was invented to simplify what I end up with on this integral that I wrote in blue. So U-substitution works like this. We're going to simplify this down by letting the variable u equal the inside function, which is g of x. And if I differentiate u, I will end up with du, which is g prime of x, because that's the derivative of g of x. Now normally we write du over dx, so we're going to actually multiply that dx to the other side. And that's because when I substitute the u and du back into this original integrand, I want to take care of this dx that's part of this integral. So now if I go ahead and rewrite this integral with the new substitution, f prime is still f prime, g of x is now u, and then this g prime of x dx is equal to du. So I'm going to substitute in du for g prime of x dx. This will result in f of g of x. Well, g of x is u, so this is f of u plus c. So the point of this is I'm starting off with something that looks very complex and very long, simplifying it down by doing a substitution and making it into something that's a lot easier to read and easier to integrate. So one of the most difficult things a lot of times with U-substitution is just recognizing what are your layers. What is the inside layer? What's the u? What's the du? So on this part, all I want to do is just break apart the layers. I'm not actually solving anything. I'm not going to take the antiderivative yet. I will do that momentarily. So if I start off with a chart, I'm going to have the first column is going to be an integral. Then I'm going to determine what is the inside function and make that my u. And then I'm going to take the derivative of the inside to calculate du. So let's start with the integral of x squared plus 1, quantity squared, 2x dx. So my inside function here is x squared plus 1 because all of that is being raised to the power of 2. So I'm going to let u equal x squared plus 1. And then to calculate du, all I'm doing is looking at what I just assigned u to equal and differentiating that to get du, which literally can stand for derivative of u. So then du is the derivative of x squared plus 1, which is 2x, and I'm going to write dx behind it. Now notice, when I compare that to the original problem, my u is x squared plus 1, which is this inside of the parentheses here, and then du is equivalent to 2x dx, which is the back part of the integrand there. And so when I go through and actually simplify this, it'll be easier to take the integral, which we'll see momentarily. But before we do that, let's look at another example. So let's say I have the integral of 5x squared plus 1 cubed times 10x dx. So I'm going to let u equal the inside function. Well, I see that 5x squared plus 1 is being raised to the third power. So I'm going to make u equal 5x squared plus 1. And then to calculate du, all I need to do is differentiate u. And so the derivative of 5x squared is 10x dx. So let's look at one more example. So let's look at the integral of 9x squared times the square root of 3x cubed minus 1 dx. So I can see my inside function is on the inside of this radical. So u will be 3x cubed minus 1. And the derivative of 3x cubed minus 1 is my du, which will equal 9x squared dx. So now that we've broken apart the layers and tried to see, okay, how do these all fit in, I want to actually go back and actually integrate each of these now. So the first one we looked at was x squared plus 1 quantity squared times 2x dx. And we said that u was going to equal x squared plus 1, and then du was the derivative of u, which went to 2x dx. Now all I want to do is actually substitute that back into the original problem, get something that's easier to integrate, and then actually integrate it. So my u was x squared plus 1, which is the inside of the parentheses here. And so I will have the integral of now u being raised to the second power. And then du is equivalent to 2x dx, which is in the original problem at the end. So write in the du. And so now, if I compare what I have with the simplified version to the original version looks like it has anti-chain rule, anti-product rule. It's very complex with a lot of different things happening in the original integrand. But now that I simplified it down to a different variable of u and du, I just have u squared du, and that's just going to be a regular anti-power rule where I add 1 to the exponent, divide by the exponent. So if I add 1 to the exponent, I get u to the third power over 3 plus c. And then because I did a substitution, all I have to do now is just actually go back and plug in my u. So I will have x squared plus 1 quantity cubed over 3 plus c. And that is the antiderivative of the original problem, x squared plus 1 squared 2x dx. So the same concept would apply to the next example. With this one in the chart, we determined that the inside function was 5x squared plus 1, so that's my u. The derivative of u is du, which goes to 10x dx. And so notice I have the 10x dx in the original problem, as well as the 5x squared plus 1, of course. So if I rewrite this, I have the integral of u raised to the third power still, times du at the end. Well, the antiderivative of u cubed is just u to the fourth over 4 plus c. And then if I just go back and substitute in my u, I have 1/4 5x squared plus 1 raised to the fourth plus c is my antiderivative. So looking at my third example, my inside function u was 3x cubed minus 1. The derivative of 3x cubed minus 1 is 9x squared dx. And so I have the u on the inside. I have the 9x squared dx as well. And so if I rewrite this, I have the integral of the square root of u du. Now notice the 9x squared is actually in front of the square root. We don't write du in front. It's part of notation at this point in time. And so even if it looks like du would be written in the front here, we write it behind whatever else is in the original problem. And so that way all the notation is lined up. You have the integral sign, you have the integrand, and then you have your variable of integration, the du at the end. And of course, to integrate this, I'm going to need to rewrite it. So I'm going to have the integral of u to the 1/2 du. The antiderivative would then go to 2/3 u to the 3/2 plus c. And of course, you have to go back and plug in your u, so I'm going to do that all in one step, where I plug in the 3x cubed minus 1 in for my u. And that's my antiderivative. Now all of those examples, the du fit in exactly perfectly into the original problem. But that doesn't always happen. So this last example deals with what happens when it's almost correct, but there's something that's missing. So I still start off by finding my u. My u is the inside function, x squared plus 4. To differentiate to get du, I don't look at the original problem. I just look at my u and take the derivative of u. So the derivative of x squared plus 4 is 2x dx. And here's where you should notice you have an issue. The u is in the original problem. But if I compare the du to the original, the du says I need a 2x dx. I only have an x dx. I have to have every single little piece of du in the original problem in order for the substitution to fit exactly. So if I'm just missing a coefficient, I can actually put in the coefficient that I'm missing. So I can put in the 2 I'm missing, because everything's just being multiplied on the inside. But you can't just magically multiply by 2. Mathematically, I have to balance it out. So in order to balance it out, I'm going to divide by 2 out in front. So if you're missing a coefficient for du, you can put that in on the inside to manipulate it to fit what we need for the substitution, but then you put the reciprocal being multiplied on the outside. So now if I rewrite it, I have 1/2 on the outside, u to the third, and then this 2x dx is all equal to du. Comparatively, this is going to be a lot easier to integrate than the original problem. And so now I can take the antiderivative and have 1/2 times 1/4 u to the fourth plus c, which will give me 1/8 u, which is x squared plus 4, to the fourth plus c. And there's my antiderivative. So if you're missing just a coefficient, then you're allowed to put that in as long as you put the reciprocal out in front. However, if I'm missing a variable, a function of x, I cannot just multiply by x and then divide by x. I will actually have to pick a different u for the u substitution or pick a different method. Here's what I mean by that. Let's say I had something like x squared minus 3 to the fourth dx. Well, u would still be the inside, so u would be x squared minus 3. And then du is the derivative of the u. So that would give me 2x dx. I'm missing the 2x in this original problem. So I have the u is here with the parentheses, but for the du, all I have is the dx. If I was just missing the coefficient of 2, I could put that in and then divide by 2 out in front. However, because I'm missing a function of x, u substitution, where u is x squared minus 3, will not work, which means I either have to pick a different u or find a different method, or it's possible that you can't actually integrate this by hand. In this case, what I would need to do is actually multiply this out 4 times, and so expand that polynomial. Then I can find the antiderivative after that. So we'll look at other methods as well later on.